Alright, I've got an example here of vector curl and in particular Stokes theorem. So I've got a field A which is given in cylindrical coordinates with a rho and a phi, no az component there, and we're going to evaluate the closed line integral a dot dl around this path shown in blue. So that's L, the path shown in blue. Notice the direction of the arrows. And then we're going to verify Stokes theorem. So let's first recall what Stokes theorem says. Stokes theorem relates a closed line integral a dot dl with a surface integral of the curl of that vector field, right? ds there. We need, we need dot ds. Okay, so that is Stokes theorem. So in order to verify Stokes theorem, we are going to calculate both sides of this equation, and hopefully we get the same value. So we're going to start with the left. Calculate the closed line integral of a dot dl. Alright, so let's do that. The closed line integral of a dot dl is equal to, and you'll notice that I've labeled the different segments here of our path, 1, 2, 3, 4. Now, if the original figure was not labeled with segments, you have to understand that you have to break that up into individual segments. So we're going to integrate our line over segment 1, a dot dl, okay, plus we're going to do the integral over segment 2, a dot dl, plus segment 3, a dot dl, plus segment 4, a dot dl. Okay, so let's start with segment 1. So when you integrate, the key is to ask yourself what is changing as I go along that path, or along the volume, or along the surface area. So what's changing along this path? Rho is not changing because rho is constant at 5. Okay, what is changing here, and it's not z because we're in the xy plane, so what is changing here is the angle. The angle changes from 30 or pi over 6 to 60 degrees or pi over 3. So in this case, okay, we've got our change in length, the displacement vector dl is just rho d phi times a phi. So let me write that down. So dl in this case is rho d phi a phi, right? And so what we've got in this case, when we integrate over segment 1, a dot dl, a is rho cosine phi, it's given in the problem, a rho, plus sine phi, a phi, that's a, right, dotted with rho d phi, a phi. Okay, so we do that, and we note that a phi dotted with a rho is 0 because they are orthogonal. And then a phi dotted with itself is 1, again, because it has a unit length. So what we get here, I'm going to leave off the bounds for right now, is rho sine phi d phi, like this. Okay, and we said what is changing here? Phi is changing. Phi goes from pi over 6 or 30 degrees to pi over 3, 60 degrees. Okay, and the order of those things matters, right? Because notice the orientation of the path. We're going from 30 degrees to 60 degrees. So that matters here. I'm going to put phi is that. And in this case, rho is 5. Rho is held constant at 5. So we're going to say that this is 5 times the integral of sine of phi d phi, and the integral is then minus cosine phi, right, when we integrate sine of phi. And we're going to plug in pi over 6, and we're going to plug in pi over 3. So what do we do when we plug that in? We get 5 times, and when I plug in, so because of the negative sign, I'm going to plug in the lower bound first. So this is square root of 3 over 2, right? The cosine of pi over 6 minus, and then the cosine of pi over 3 is 1/2. So for this segment, I've got 5 square root of 3 minus 5 over 2. Okay, moving along then, we're going to go to segment 2. So again, what is changing in segment 2? Well, in this case, the angle is held constant, and it's rho. It's the radius that changes. So in this case, dl is just d rho times a unit vector in the rho direction. So let me write that. Okay, so now we're going to evaluate a dot dl. Okay, and again, a is this rho cosine phi a rho plus sine phi a phi, like this, dotted with d rho a rho, like this. Okay, so when I dot a rho with a phi, those are orthogonal, and so I get 0 there. And when I dot a rho with a rho, I get 1. And so this becomes, and I left off the bounds here, so let me just put 2. This becomes rho cosine phi d rho now. And so this is rho. Rho changes from 5 to 2, and the order matters. It's a little weird writing from 5 to 2, but it's true. Rho is going from 5 to 2. So cosine phi here is a constant, so it can come out of the integral, and phi is held constant at 60 degrees. So the cosine of 60 degrees, and we said this before, was 1/2, right? And then, so when I integrate phi, I get 1/2 phi squared. Okay, evaluated from 5 to 2. So when I plug in the 2, I get 2 squared is 4, and I get 1, and then minus, okay, 25 over 4. 25 over 4 there. So 1 is 4 over 4. So I've got 4 over 4 minus 25, so that's minus 21 over 4. Okay. Now let's consider path 3. So path 3 here, what is changing? Well, it is the angle that's changing from 60 degrees to 30 degrees here. So I'm going to do this one a little bit quicker. The angle changes from, again, 30 degrees, which is pi over 3, to pi over 6. And then A is up here, and dl, so here's dl when the angle changes. And so when I dot that with A, again we did it over here actually, I get rho sine phi d phi. Okay, and again, because that's a phi is orthogonal to a rho, and so it only picks up the sine phi part of this. Okay, so now rho is held constant at 2, so that 2 can come out, and then when we integrate, we get minus cosine of phi from pi over 6, or from pi over 3 to pi over 6, right? Okay, so I plug in the lower bound first because of the minus sign. So this is 2 times cosine of pi over 3 is the square root of 3. Or no, the cosine of pi over 3 is, square root of 3 over 2. And then we've got cosine of pi over 6. Oh no, excuse me. Cosine of pi over 3 is 1/2, right? Cosine of pi over 3 is 1/2, and then the cosine of pi over 6 is square root of 3 over 2, and so I get 1 minus the square root of 3. Okay, now let's do 4, segment 4, and again I'm going to do segment 4 quickly. like I did segment 3. And what is changing in segment 4? That's the radius. Okay, so for when the radius changes, dl is this thing, d rho a rho, just like we had in segment 2. Okay, so now we've got rho goes from 2 to 5. And when I take a dot dl, just like we did in segment 2, right, I get rho cosine phi d rho, like that. Okay, and here cosine phi is constant, right, and phi is 30 degrees, or pi over 6, so that is the square root of 3 over 2 times the integral of rho is 1/2 rho squared, right, from rho goes from 2 to 5, like that. Okay, and so we've got the square root of 3 over 2 times 1/2, so square root of 3 over 4, and then I've got 25 minus 4. So 25 minus 4 is 21, so this is 21 square root of 3 over 4. Okay, phew. So now, remember the idea was that we're calculating the closed line integral, and so we need to add these 3 pieces, or these 4 pieces, excuse me, up. So when I add those up, I get 4.94. 4.94. So just to be clear, that's the sum of this, 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 and this. When I add those 4 pieces up, I get 4.94 up to 3 significant digits. Okay, so I'm going to erase this work. Feel free to pause the video if you need to. Okay. So that was the left side of Stokes' theorem. I'm going to save the answer. Left side of Stokes' theorem. All right, so now we're going to try the right side, and hopefully we get the same thing, right? Because we have this equal sign. This is Stokes' theorem. So Stokes' theorem now says that we can instead calculate the closed line integral as a surface integral. So what surface do we mean? Well, that's the surface S. So now imagine this thing is closed. Okay, and it's a surface. So we're going to integrate over that surface, and we're going to integrate the curl of the vector field over that surface. Oh, okay, so how do we do that? Well, first of all, let's calculate the curl of A. So we are in cylindrical coordinates, so we need a 1 over rho there, and then we put a rho up here, and we put rho a phi there, and we put a z there. Then we have the partials here in the next row. Like this. And then we put the rho component of the vector field here. So this is rho cosine phi. And then here we put rho times the phi component. So this is rho times sine phi. Okay, that's a subtle detail that we need to be aware of. That's rho times the phi component, just like we had rho times the phi component up here. And then we put the z component of our vector field, which happens to be 0 in this case. All right, so let me compute this curl then. So I've got 1 over rho times everything, the determinant here. So I've got, start with a rho. I'll assume you know how to do this by now. So we've got the partial on this should be phi, not theta, excuse me. That's a phi. The partial on phi is 0, so that's 0. Partial on z here, so that's also 0, so that's nice, right? Okay, that's in the rho direction. Nice. Then we've got minus rho times the partial on rho was 0, that's 0. And then the partial on z with rho cosine phi, that's 0 too, that's nice. That was in the phi direction. Plus, then we have the partial on rho of rho sine theta. So we pick up a sine theta there. And then minus the partial on phi of rho cosine phi. So we pick up a plus. That makes that a plus rho sine phi in the z direction. So that's good. And our curl, then we've got this 1 over rho here. All of this is 0. And we've got 1 over rho. I guess the sine can come out, right? Times the sine of phi times 1 plus rho in the z direction. Okay, that's really nice. So that's our curl. But now we need to evaluate the surface integral of that curl. Okay, so here's our curl, and when we dot it with ds, what are we going to have? We're going to have a little bit of simplification. But let's first talk about ds in this case. So we ask ourselves, what is changing on that surface? Well, for a surface, two things change. Z does not change because we're in the xy plane. So the only thing that's changing here, the only two things that are changing, of course, the radius changes from 2 to 5, and the angle changes from 30 degrees to 60 degrees, right? So our ds in this case is rho d rho d phi times a normal vector d az, right? Okay, so now when we dot that with our curl, right? So we're let's be clear here. We're evaluating now the surface integral of the curl of A dot ds. Okay, this is what we're doing now. And so when we dot this vector, which is the curl, with this surface, they're parallel. Az dotted with az is 1. So what I've got here is 1 over rho times rho, so that cancels, that's nice. And then I have sine phi 1 plus rho d phi. And I ask myself, well, how are rho and phi changing? Well, phi changes from pi over 6 to pi over 3. Okay, and rho changes from 2 to 5. All right, so let me evaluate these integrals now. So I'm gonna hold phi. I'm not going to do anything with phi for the moment. I'm going to integrate rho. So I've got sine phi times rho, and then plus 1/2 rho squared sine phi, right? And rho goes from 2 to 5, rho d phi. So when I do that, okay, I plug in 5 for rho, so I've got 5 sine phi plus 25 halves sine phi, and then minus, what I get when I plug in rho is 2, so I get 2 sine phi, and then 4, 2, so this becomes minus 2 sine phi d phi. Okay, did we do that correct? 2, 4, minus, become minus? I think so. All right, so now we need to integrate that with respect to phi. So 5 sine phi, that becomes minus 5 cosine phi. Okay, 25 halves becomes minus 25 halves cosine phi. You know, we could combine these things, by the way. Minus 2 sine phi becomes plus 2 cosine phi. And again, minus 2 sine phi becomes plus 2 cosine phi. All right, and we're going to plug in pi over 6 and pi over 3. Okay, so when we do that, remember that the cosine of pi over 3 is square root of 3 over 2, and the cosine of pi over 6 is 1/2. So when we do that, we get 4.94, and that is the answer, and therefore we have verified Stokes' theorem.